Okay, so you can imagine that we can keep stacking more and more of these functions, but because we're kind of using the results of the function and then running the function again, this brings up a really powerful way of doing programming where the function can actually call itself. So to show you how this works, I'm going to add in one more input into this function, which will specify the depth of my recursion. So just like with while loops, it's really important to have a way where the function can start calling itself, but only for a limited time, that there's a way that it can actually break out of that infinite loop. And we're going to do that by always keeping track of how many times the recursion has run. Okay, so to start, I'm going to call this function. I'm going to pass in my first point, and then I'm going to also pass it the integer 0 to specify that this is the first time that the function is running. So now that 0 is going to be passed into this recursion input. Alright, and we're going to adapt our code a little bit. We're going to keep this part where basically every time the function is run, the point is automatically added to our list. And then the rest of the function we're going to actually wrap in a conditional to test whether our recursion has executed the maximum number of times that we want. So here we're going to say if recursion is less than 10, colon, and then we're going to move this operation into the condition. So here it's going to basically execute the function. If recursion value is less than 10, it's going to move that point. And then the key factor here is once it creates the moved point, it's actually going to call the same function again. So it's going to call itself again, but this time on the moved point. And then the most important part is that when we call that function again, we pass a higher version of the recursion. Okay, so if recursion is 0 on the first time, here we're going to add 1 to the recursion level. So when the function runs again, it's going to have a new point, but it's also going to have recursion as 1. And as it goes through these functions, it's going to keep calling itself, but at some point it's going to reach this maximum of 10 and exit out of the function. And then before run, we're also going to remove this return statement because we don't need to return anything out of this function. So now we hit test, and you see now we have 10 boxes, and those are generated from the points that are output from this recurring function. Okay, so first it might not seem so obvious about what the advantages of calling this function within the function itself. You can do the same thing basically with a loop. But the great thing about this is that you can actually call this function multiple times. So instead of just calling it once, we can actually call the function twice. And the first time, we're going to move the point 2 units up and call the function. And we're going to copy this. And then move the points 2 up and over 2. And then run the function again, now on this new version of the moved point. Okay, so here we're creating a new point, running the function, creating another new point. Just to keep this clear, I can rename these variables move point 1, move point 2, and each time passing a higher value for recursion. So if we hit test now, you can see it's created this kind of growing recursive geometry where each time you get more and more geometry. And recursion is a really powerful way of building these functions, but you got to really keep track of what you're doing because it can really quickly spiral out of control. So here, just through those 10 runs, we created 2,047 pieces of geometry, because you can think of this as kind of escalating higher and higher. But the first time you run it, it runs this 2 times, but now for each of those 2 times, it runs 2 more. So for 10 runs, we actually get 2 to the power 10 pieces of geometry. Alright, so that's our basic setup, and now to make our particular branching geometry, I'm just going to add some more features or some more control into this script. Okay, so I'll hit OK. The first thing I'm going to do is link this box size component to the distance that my points are being moved in my script. So I'm going to enter that as an input into my Python node, and I'm going to rename that to size. So this will drive the size of my boxes. And now I can reference that size here and basically set anytime I'm moving my box, change those to size and hit OK. You can see now the amount that my points are moving is related to the size of my boxes. Okay, so the next thing I'm going to do is I actually want to input a bit of randomness to how these boxes are stacking or moving in the XY plane as the structure builds up. So for that I need to import another library, which is the random library from Python. So type import random, and now I can use the random functions to create random numbers just like we did in Grasshopper. At the top of my function, I'm going to create two variables, one called moveX. And here I'm going to use the uniform function from the random library to basically create a random number within some bounds of A and B. So to start, I can just specify, I always want it to move from 0 to the size of the box. And so it's going to offset some random number at most the dimension of the box. And then I'm going to create another variable called moveY and do the same thing. So this is going to create two variables for how my box is moving. I'm still going to move it up the size of the box, but here I'm going to pass in these two variables. And then I'm going to comment out this second call for now just to see what's happening. You can see now we have this more random stacking logic where they're always moving some amount. But since I don't want it to just move in one direction, I'm actually going to feed in my size as the lowest limit and the highest limit into the random function. So now I get more of this random stacking. And if I want even more control over how that stacking is happening, I can add a multiplier to these sizes to control the extent of that random motion. So here I'm going to create a new variable called move factor. I'm just going to multiply all of these size variables by that factor. So when it's 1, it's going to move at the ultimate extent, but I can scale that factor down to create less offset. I'm going to hit OK. I'm going to create a new input, which is going to be that move factor. So I'm going to name it the same thing I did in my script. And now I can plug in a real number into that input, and that's going to control how much my geometry is offsetting. So if I set this to 0, the geometry goes straight up. And if I set it to 1, it's at the maximum offset. Okay, so you might notice that as I change this number, it's not that they're just sliding more or less. The entire kind of composition of the stack changes, and that's because every time I change an input, the random factors change. And in order to control that, we have to use the seed number. And the seed value for a random function basically dictates how that function is executed. And if you don't set the seed manually, the seed gets regenerated every time. But if we set it manually at the top of our script, so here we'll type in random.seed, then whatever we set this number to, if it remains constant, we're always going to get the same result. So here we're going to create another input called random seed. We're going to feed that into the seed function. And then we're going to add a new input. And then seeds can be any integer. So typically you just set it some very high number. And then here we're going to rename that to random seed and hit run. So now this is setting our seed, so if we move it, we get a new result every time. But if this number stays the same, then while we make changes to other parameters, it doesn't regenerate that solution. So now we can keep one design, but then change the way that the boxes are being stacked. Okay, so now we have most of our generative geometry function built. The last thing I'm going to do is reincorporate the second function call to create a branching logic within my function. But I don't want to do this every time. I don't want to branch and create more and more geometry every time. I just want to do this in specific cases. And what I'm going to do is create a conditional that basically triggers the second function if a certain minimum offset has been reached. So the idea here is that sometimes the stacking is pretty much on top of the other box, so in that case there won't be any branching, but as soon as the box moves far enough along, I'm going to create another box right next to it, which is mirrored from this first box. I'm going to create a conditional and say if the absolute value of move x, so here's the absolute value, so I'm basically saying if this move x parameter reaches a value either positive or negative that's bigger than the size of the box times 0.5, so if it reaches the value that's more than half the box dimension in the x direction, and if the same is true for the move y value, then I will create the second point, and I'm going to call this function again on the second point, which is basically going to create a new branch for my logic. So once that point is created and that box is created, it doesn't just create the box, it relaunches this whole function starting at that point, so it's going to branch off from there. And the last thing I have to do is change the logic for how this second point is being created. Instead of just moving it over by the size, I want to move it the inverse of how I moved the first point. So to do that, I just use the same move x and y variables, but I'm just going to make them negative, which will give me the mirrored image. Okay, so I can go to test, and you can see what's happened. Basically, at this level, the box was more than halfway over, so it created another box as a mirrored image, and then started going up from there and creating its own branch. And because of the way we've set up our inputs, we can actually start to control how much of that branching is happening just by changing this factor. So as we make the factor smaller, it's less likely that they're going to move far enough over. As we increase it, we can get more and more of the branching. We can also change our random seed to give us new iterations of designs. And you can imagine extending this script even more to put in more logic for how the branching happening. But that's all I'm going to do for this example. And now we have sort of this very simple system set up through the script to create this fairly complex geometry that would be either impossible or at least very difficult to create just through the basic Grasshopper. But it's important to see that we're not doing everything through the script. We're only doing the specific logic and creation functions that are particularly useful to do in Python. But everything else, like the inputs and processing geometry, is still happening within Grasshopper the same way.